All right, let's talk about one of the absolute cornerstones of modern software development. I'm talking about object-oriented programming, or, as you'll almost always hear it, OOP. And you know, this isn't just some academic question. This is the real-world problem that every single major software project runs into. I mean, think about it. As your code gets bigger and bigger, how on earth do you keep it organized? How do you keep it from turning into a complete mess? Well, the answer lies in a pretty brilliant way of thinking about design.
And that way of thinking is object-oriented programming. At its heart, it's really just a blueprint. It helps developers structure their code by modeling it after things in the real world. So in OOP, an object isn't just a physical thing, it's this neat, self-contained little package of code that has its own data and its own abilities, which makes everything feel way more logical and intuitive.
So here's our game plan. We're going to dive into the 4 core principles, the 4 pillars really, that hold this whole idea together. We've got encapsulation, inheritance, polymorphism, and abstraction. We're going to break down what each one is, and more importantly, why you should care.
First up, we've got the pillar that basically acts like a security guard for our code, encapsulation. This one is all about creating these safe, self-contained little bundles.
So what is it, really? Well, imagine taking your important data and all the code that's allowed to touch that data and locking them up together in a protective capsule. In programming, we call that capsule a class. And the whole point of this is to stop anyone or any other piece of code from just reaching in and messing with the data directly.
And why would we want to do that? Simple. It's all about control and safety. This protects your data from being changed by accident. It keeps sensitive information under wraps, and it just makes your code way more flexible. I mean, if you need to change how something works on the inside, you can do it. And as long as you don't change the public-facing controls, nothing else in your application breaks. It's fantastic.
You actually see this idea everywhere in real life. Take your phone. You can't just open it up and start fiddling with the battery or the circuits, right? All that complex stuff is hidden away. Instead, you're given a really simple public interface, the power button, the volume buttons, to interact with it safely. It's the exact same idea in code. An employee's salary, you make that private, hidden from the outside world. If you want to view it or change it, you have to go through designated public methods like getSalary or setSalary. And those methods can have rules like, hey, you can't set a salary to a negative number. It gives you total control.
Okay, so encapsulation gives us these secure, self-contained objects. That's great. But what if we want to make new objects that are just a little bit different from ones we already have? Do we have to start from scratch? Nope. And that's where our second pillar, inheritance, comes into play.
Inheritance is this amazing feature that lets you build a new class that's basically a specialized version of an existing one. We call the new one the child and the existing one the parent. The child automatically gets all the features of the parent, which is a huge deal for not having to write the same code over and over again.
This creates what programmers call an is-a relationship. So, for example, a dog is an animal. That makes sense, right? So if our parent animal class has a function, an action called eat, FO, then our dog class automatically knows how to eat, without us having to write a single extra line of code for it. It just inherits that ability.
You know, a perfect analogy for this is just simple genetics. A child inherits traits like eye color or height from their parents. Well, it works the same way in code. A child class inherits methods and data from its parent class. This keeps our code really efficient and, honestly, just a lot easier to understand.
So, inheritance lets us build these families of related objects. But what happens when different members of the family need to do the same thing, but in their own unique way? This leads us to our third and maybe most powerful pillar, polymorphism.
The name sounds super complicated, but the idea is actually pretty straightforward. It just means many forms. So in practice, you could have one single command, like draw. But with polymorphism, that one command can tell a circle object to draw a circle, a square object to draw a square, and a triangle object to draw a triangle. One name, many different outcomes depending on the object. See? Powerful.
Now, there are 2 main ways this magic happens. The first is called method overloading, which gets figured out before the program even runs. The second is method overwriting, and that happens while the program is actually running. Let's look at an example of each one.
Okay, first, overloading. This is when you have different functions that have the exact same name, but they take different kinds of inputs. Think about how you say hello. You might say, hey, what's up to a friend, but hello, how are you to a stranger? Same basic action, greeting someone, but it changes based on the context. In code, you could have an add method. One version adds 2 whole numbers. Another version adds 3 whole numbers.
and another one adds 2 decimal numbers. Same name, add, but they all work a little differently. Then we have overriding. Now this is when a child class takes a method it inherited from its parent and provides its own special version of it. So the action start engine is a general idea, but a car, a motorcycle, and a giant truck are all going to sound very different when they do it. In our code, a dog and a cat both inherit a sound method from the animal class, but the dog's version of sounding is going to make a bark, while the cat's version is going to make a meow. Same method name, but a different specialized output for each object.
So we've got secure objects that can inherit traits from each other and can perform actions in lots of different ways. But how do we use all this without getting totally lost in the details? Well, that is the job of our final pillar, abstraction.
Abstraction is all about hiding the complex, messy, internal details of how something works and only showing the essential stuff to the outside world. It lets us focus on what an object does instead of getting bogged down in how it does it.
And the whole point of this is just to make our code way, way easier to use. By hiding how things work on the inside, and you can see how this is related to encapsulation, we not only make things simpler, but we also make them more secure. Plus, it means we can go back later and totally change the internal logic. And as long as that simple public interface stays the same, no one who uses our code will ever know the difference.
Honestly, we use abstraction every single day and don't even think about it. When you drive a car, you just need to know about the steering wheel, the gas, and the brake. You're given a simple interface. You don't need to be a mechanical engineer who understands every gear in the transmission. In code, we often achieve this with something called an interface. Think of it like a contract. It guarantees that an object will have certain methods, like a start method for a vehicle. So the user just calls start, and the car starts. All the incredible complexity that makes that happen is completely hidden from view.
So there you have it. We've walked through all 4 pillars: encapsulation, inheritance, polymorphism, and abstraction. But you know, their real power isn't when they're used alone. It's how they all work together to build software that's truly solid.
See, these pillars aren't just a random list of ideas. They support each other. Encapsulation protects our objects. Inheritance lets us reuse code and build logical families. Polymorphism gives us the flexibility to let those objects behave in unique ways. And abstraction hides all that complexity, giving us a simple way to use it all. They really are a system for taming complexity.
And that system is the blueprint. It's what allows developers to build those massive, million-line applications without everything falling into total chaos. It provides the structure, the safety, and the scalability that modern software demands. So I guess the only question left is, now that you know the blueprint, what are you going to build with it?